Welcome to this problem walkthrough. Today, we'll be exploring an exciting dynamic programming challenge, problem number 1155, number of dice rolls with target sum. We'll break down the problem, analyze different approaches, and step through the solution to strengthen our understanding of key concepts. Let's dive in. In this problem, you are given n dice, and each die has k faces numbered from 1 to k. The goal is to determine how many different ways you can roll the dice so that the sum of the numbers on the faces equals the given target. Since the result could be very large, you are asked to return the answer modulo 10⁻9 plus 7. The input consists of three integers, n, the number of dice, k, the number of faces on each die, and target, the desired sum. The constraints specify that n, k, and target are within certain ranges, with up to 30 dice and 30 faces per die, and a target as high as 1000. The output is a single integer representing the number of ways to achieve the target sum under the modulo condition. For example, if there is one die with 6 faces, and the target sum is 3, the output is 1. This is because there is only one way to achieve the target, rolling a 3. In another example, with 2 dice, each having 6 faces, and a target sum of 7, the output is 6. This is because there are 6 possible pairs of rolls that add up to 7. These pairs include rolling a 1 on the first die and a 6 on the second, a 2 and a 5, and so on. The complete list of pairs to achieve a sum of 7 continues with 3, 4, 4, 3, 5, 2, and 6, 1. So, the total number of ways is 6. In a more complex scenario, if you have 30 dice, each with 30 faces, and the target sum is 500, the number of ways to achieve this is extremely large. Therefore, the result is returned as 222616187 after applying the modulo 10⁻9 plus 7. This ensures the value remains manageable and fits within standard computational limits. The constraints highlight some important edge cases. For instance, with the smallest values for n, k, and target, such as one die with one face and a target of 1, the output is 1 because there is only one combination. On the other hand, if the target is smaller than the number of dice, like having 2 dice but a target of 1, the result is 0 because it's impossible to achieve the target. Similarly, if the target exceeds the maximum possible sum, such as a target of 20 with 2 dice, each having 6 faces, the result is also 0. For large inputs, efficient computation is crucial. By using dynamic programming, we can break the problem into smaller states, where each state represents the number of ways to achieve a specific sum with a given number of dice. The modulo operation ensures calculations remain efficient, even for the largest inputs. To tackle the problem, one approach we might first consider is brute force. This is a straightforward method where we enumerate all possible outcomes of rolling n dice. Each die has k faces, meaning there are k⁻n total combinations for n dice. For each combination, we calculate the sum and count how many of these sums match the target value. While this approach is simple to understand, it quickly becomes impractical as n and k grow. The number of combinations increases exponentially, making this approach computationally prohibitive for large inputs. For instance, if n is 30 and k is 6, the total combinations, 6⁻30, become astronomically large, and evaluating all of them would be infeasible. Therefore, while the brute force method gives us a theoretical baseline, it's not suitable for solving the problem efficiently. To address this, we turn to dynamic programming, which relies on breaking the problem into smaller, overlapping subproblems. By defining dp, I, j, as the number of ways to roll I dice to achieve a sum of j, we can build solutions incrementally. The key transition here is that to calculate dp, I, j, we consider all possible outcomes for the last die, summing up contributions from dp, I1, j1, dp, I1, j2, and so on, up to dp, I1, jk, for all valid values of the last die. This reduces the need to generate all combinations explicitly while still capturing the same result. Now, let's refine the dynamic programming approach by considering the base case and optimizing the transition. The base case is straightforward. There's exactly one way to achieve a sum of 0 with 0 dice, so dp, 0, 0, equals 1. For all other cases, such as when there's a positive sum or dice count, the value is 0. The next challenge is optimizing the transition relation. Instead of summing over k terms at each step, which can be inefficient, we use a sliding window technique. This technique allows us to compute the transition in constant time by maintaining a running sum. The formula becomes dp I(j) equals dp I(j1) plus dp I1j dp I1jk1, where the last term ensures we exclude contributions that fall out of the valid range. This optimization drastically reduces the computational overhead, allowing us to calculate each dp I(j) in O1 time. By applying this technique, the overall time complexity of the solution becomes O(n*min) target n*k, and the space complexity is O(n** target. Further, with additional optimizations, the space complexity can be reduced to O target, making the solution even more memory efficient. These improvements highlight the power of dynamic programming over brute force, especially for handling large constraints effectively. Dynamic programming stands out as the optimal strategy for this problem for several reasons. First, it scales efficiently with large values of n, k, and target, unlike the brute force approach. Second, memoization allows us to avoid redundant calculations by reusing intermediate results, which significantly reduces computational overhead. While the dynamic programming solution does require additional memory, this trade-off is justified given the dramatic improvement in time complexity. The pivotal insight that made this approach even more efficient was the use of a sliding window to optimize the transition relation. This reduced the potential bottleneck of summing over k terms, transforming a slower solution into one that is computationally efficient and scalable. In conclusion, dynamic programming not only balances clarity and efficiency but also ensures the solution is robust enough to handle the problem's constraints. This makes it the definitive choice for solving the problem effectively. To solve the problem of enumerating all possible outcomes of rolling n dice with k faces, we can start by breaking it down into clear steps. First, we need to understand the scope of the problem. When rolling n dice, each die having k faces, there are k(n) possible combinations of outcomes. Each outcome can be represented as a list of integers, where the length of the list equals the number of dice, n, and each integer in the list is a value between 1 and k, inclusive. For instance, if n equals 2 and k equals 3, our outcomes would include lists like 1 1, 1 2, 1 3, 2 1, and so forth. To generate these combinations, we'll use a systematic approach. One effective method is recursion, where at each step we append a possible face value to the current outcome list until it reaches the desired length of n. Recursion suits this problem well since it can handle arbitrary values of n and k, though iterative methods, like nested loops, could also be used for smaller values of n and k. Next, we delve into implementing recursive backtracking to generate all possible outcomes. We start with an empty list to represent the current outcome. At each recursive level, we iterate over all possible face values, from 1 to k, appending each value to the list. Once the list reaches length n, meaning we have a complete outcome, we add it to the result list. We then backtrack by removing the last added value, allowing us to explore other possibilities in the same recursive branch. This ensures we systematically generate every valid combination. The recursion depth corresponds to the number of dice, n, and at each level, we explore k possibilities. The time complexity for this brute force approach is k to the power of n, since we explore all combinations exhaustively. It's important to note that we don't prune the search space in this method because every combination is required. Special cases include scenarios like n equals 0, where no dice are rolled, resulting in an empty output list, or k equals 1, where all outcomes are the same repeated value, such as 1, 1, 1. To implement this approach, we make strategic use of data structures. The result list is used to collect all valid outcomes, and each outcome is represented as a list of integers. For example, if n equals 2 and k equals 2, the result list would contain 1 1, 1 2, 2 1, 2 2. During the recursion, we maintain a temporary list to build the current outcome. This temporary list allows us to construct combinations dynamically while avoiding unnecessary memory allocations. For each recursive call, we add one possible face value to the temporary list. When the base case is reached, meaning the temporary list's length equals n, we append a copy of this list to the result list. Afterward, we backtrack by removing the last value, effectively resetting the state to explore other options. This combination of recursive calls and backtracking ensures that every possible outcome is generated efficiently and without duplication.
Here's the Python implementation of the recursive backtracking approach.
The function roll_dice accepts two parameters, n and k, representing the number of dice and the number of faces, respectively. Inside, we define a helper function backtrack, which performs the recursive generation.
The base case checks if the current list's length equals n. If so, we add a copy of the list to the result list, outcomes, and return.
Otherwise, we iterate through each possible face value, from 1 to k. For each value, we append it to the current list, make a recursive call to explore further, and then backtrack by removing the last value.
This ensures we explore all combinations systematically.
Finally, the roll_dice function initializes the result list, calls the helper function with an empty outcome, and returns the complete list of outcomes. The example usage demonstrates the function with n equals 2 and k equals 3, generating all valid 2 dice rolls with 3 faces per die. To see how this algorithm works in practice, let's walk through an example with n equals 2 and k equals 3.
We start with an empty list as the current outcome. First, we add 1, creating 1, and recurse. Then, we add another 1, forming 1, 1. Since this list has reached the desired length of n, we add it to the result list and backtrack by removing the last value, returning to 1. Next, we add 2 to form 1, 2, which is another complete outcome, so we add it to the results and backtrack again. This process continues until we've explored all possible face values for the current die. Once all options for the first die have been exhausted, we backtrack to an empty list and start with 2, repeating the process for combinations starting with 2. Eventually, we generate every possible outcome, which for this case is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. This systematic exploration ensures that no combination is missed. This solution uses dynamic programming, DP, to solve the problem of counting the number of ways to roll in dice so that their sum equals a given target. Here's the step-by-step explanation.
1. Initialization. We define a modulo constant, 10 to the power of 9 plus 7, to ensure the results fit within integer limits. A 2D DP table DP is created where DP, dice, t, represents the number of ways to achieve a sum t using dice. Initially, DP 0, 0 equals 1 represents the base case, one way to achieve a sum of 0 with 0 dice. 2. Outer loop, number of dice, we iterate over the number of dice, from 1 to n. 3. Middle loop, target sum, for each dice count, we iterate over all possible target sums, from 1 to target. For inner loop, die faces, for each target sum, we iterate over all possible face values, 1 to k. If the current face value is valid, i.e., less than or equal to the target sum, we update DP, dice, t, by adding the number of ways to achieve t face using dice, 1 dice. This ensures we're building the solution incrementally. 5. Modulo operation. After each update, we apply the modulo operation to keep the results bounded. 6. Final result. Once the loop's complete, DP, n, target, contains the desired result, the number of ways to roll in dice so their sum equals target. This approach is efficient with a time complexity of O, n asterisk target asterisk k, and a space complexity of O, n asterisk target. It ensures all edge cases, such as invalid inputs, e.g., target n or target n asterisk k, are handled implicitly by the DP formulation. This is the Java implementation of the LeetCode problem number 1155, number of dice rolls with target sum. The logic mirrors the Python solution, using a dynamic programming approach with a 2D table where DP, dice, target, represents the number of ways to achieve the target sum with the given number of dice. Key differences include explicit type declarations for variables, the use of modular arithmetic to prevent overflow, and the Java-specific syntax for arrays and loops. In this example, we aim to determine the number of ways to roll 2 6-sided dice to achieve a target sum of 7. To solve this, we use a dynamic programming approach. First, we initialize a 2D DP table, DP, where DP, I, t, represents the number of ways to achieve a sum of t using I dice. This table has dimensions, n plus 1 x, target plus 1, and is initially filled with zeros. The base case is DP 0, 0 equals 1, which indicates that there's exactly one way to achieve a sum of 0 with 0 dice. We also define a modulus constant, mod equals 10 to the power of 9 plus 7, to handle large numbers and prevent overflow.
Next, we process the dice one by one.
For the first die, we iterate through possible face values, from 1 to 6, and update the table based on the previous row. For example, dp 1, 1 equals dp 0, 0 equals 1, and for other targets like dp 1, 2, or dp 1, 6, the values remain 0 because no previous configuration allows those sums. After processing the first die, the row dp 1 becomes 0, 1, 1, 1, 1, 1, 1, which captures all the sums achievable with one die. Moving to the second die, we calculate the number of ways to achieve each target sum, considering all combinations of the first die's results and the second die's face values. For instance, to achieve a sum of 7, we sum contributions from dp 1, 6, dp 1, 5, and so on. After applying the modulus, the final state of dp 2 is 0, 0, 1, 2, 3, 4, 5, 6, which means there are 6 ways to achieve a sum of 7 with 2 dice. From the previous example, we know the dynamic programming approach works well for multiple dice. Now, we extend this to 3 6-sided dice with a target sum of 10. As before, we initialize a dp table of size 4x11 and set dp 0, 0 equals 1 as the base case. For the first die, we iterate through face values and update the table, resulting in dp 1 equals 0, 1, 1, 1, 1, 1, 1, representing possible sums achievable with one die. Next, we process the second die, considering sums up to 10. Using the same logic as before, we update dp 2 by summing contributions from previous results. For example, achieving a sum of 10 involves summing contributions from dp 1, 9, dp 1, 8, and so on. This gives us dp 2 equals 0, 0, 1, 2, 3, 4, 5, 6, 5, 4, 3. Finally, for the third die, we extend this approach to calculate contributions for sums up to 10. Specifically, for dp 3, 10, we sum results from dp 2, 9, down to dp 2, 4, accounting for all possible face values. After completing the updates, the final state of dp 3 includes 27 ways to achieve a sum of 10 with 3 dice. Now, we consider a simpler case with only one 6-sided die and a target sum of 3. As usual, we start by initializing a dp table. This time, the table has dimensions 2x4 to account for one die and a maximum target sum of 3. We set dp 0, 0 equals 1 as the base case, indicating one way to achieve a sum of 0 with 0 dice. For the single die, we calculate the number of ways to achieve the target sum of 3. Since there's only one die, we directly update dp 1, 3, based on contributions from dp 0, 2, dp 0, 1, and dp 0, 0. Here, dp 1, 3 equals dp 0, 2 plus dp 0, 1 plus dp 0, 0, which equals 1. This result makes sense because there's exactly one way to roll a single die and get a sum of 3 by rolling a 3. Thus, the output for this example is one way to achieve the target sum of 3 with one die. Here, we analyze the time complexity of the dynamic programming solution. The algorithm relies on 3 nested loops. The outermost loop iterates through the number of dice, represented as n. For each dice roll, the second loop iterates over all possible target sums from 1 to the given target, contributing O, target, iterations. Finally, the innermost loop goes through all the possible face values of the dice, from 1 to k, adding O, k, iterations. When we combine these 3 loops, the total number of iterations becomes O, n, *O, target, *O, k, which simplifies to O, n target *k. This represents the overall time complexity of the solution, highlighting how the number of dice, the target sum, and the number of faces on the dice all contribute to the computational cost. Each iteration within the loops performs constant time operations, such as additions and modulo calculations. This means there's no additional hidden cost beyond the loop structure itself. Therefore, the overall time complexity remains O, n target k. Now, turning to the space complexity, the solution uses a 2D dynamic programming table, DP, to store intermediate results. This table has dimensions, n plus 1, target plus 1, where n plus 1 accounts for the dice, including the base case with 0 dice, and target plus 1 accounts for all possible sums, starting from 0. The memory required for this table is proportional to the product of these dimensions, resulting in a space complexity of O, n asterisk target. In addition to the DP table, the algorithm uses a few other variables such as mod, dice, t, and face. These consume negligible space and are considered O1 in terms of complexity. Thus, the overall space complexity remains O, n asterisk target. Comparing this to a brute force approach, a naive solution would involve recursively exploring all possible combinations of dice rolls and summing their outcomes. With n dice, each having k faces, there are k-n combinations to examine. Checking each combination for the target sum would result in an exponential time complexity of O, k to the power of n, which is computationally expensive. In contrast, our dynamic programming solution reduces this to O, n asterisk target asterisk k, by avoiding redundant computations through the use of the DP table. By iterating over dice and target states, the dynamic programming solution constructs the final result efficiently, avoiding the need to explore all k-n combinations. This makes it significantly faster and more practical for larger inputs. The time and space complexities remain consistent across the best, average, and worst cases, as the algorithm always processes all n asterisk target asterisk k states, regardless of the input values. In summary, the dynamic programming approach boasts a time complexity of O, n asterisk target asterisk k, and a space complexity of O, n asterisk target. Compared to the exponential O, k to the power of n, complexity of the naive solution, this method is far more scalable, though extremely large inputs could still present performance challenges due to its cubic time complexity.
Overall, this approach strikes an excellent balance between efficiency and robustness for moderate-sized problems. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases can be a big pitfall. For instance, when the number of dice, n, is 0 or when there's only one face on each die, k equals 1, many solutions fail to handle these scenarios properly. This often leads to runtime errors or incorrect outputs, especially in recursive or dynamic programming solutions. Another frequent issue is using an inefficient brute force implementation, where all possible outcomes for n dice are generated without any optimization. This approach has an exponential time complexity of O, k to the power of n, which quickly becomes impractical for larger values of n or k. Additionally, double counting in recursive approaches is a common error. Without memoization, repetitive calculations occur, causing the recursion tree to expand unnecessarily, which significantly impacts performance. Lastly, incorrect base cases in dynamic programming solutions can also cause problems. For example, if you initialize DP 0, 0 incorrectly or fail to set up other base states properly, it can lead to cascading errors throughout the solution. Dynamic programming relies heavily on accurate base case initialization, so getting this part right is critical. Misinterpreting the problem statement is another common challenge. For example, some may confuse the number of dice, n, with the number of faces, k, or misunderstand the constraints altogether. Such misinterpretations can lead to crafting an entirely incorrect solution, wasting valuable time, especially in an interview. Speaking of interviews, it's helpful to recognize patterns in problems involving dice rolls, coin flips, or other combinatorial setups. These are often best approached using dynamic programming or probability theory by breaking the problem into smaller, manageable subproblems. It's also important to weigh trade-offs in your approach.
For small input sizes, a brute force solution might be acceptable, but for larger constraints, optimization using dynamic programming or memoization becomes essential. Additionally, make sure to communicate your reasoning clearly to the interviewer. For instance, explain why you might start with a recursive approach for simplicity, even if it's not the most efficient method. Finally, look for optimization opportunities, such as symmetries or invariants in the problem, which can help reduce the state space and make your solution more efficient. This problem also connects to several related problems that you might encounter. For instance, LeetCode 1155, number of dice rolls with target sum, is the exact problem we're discussing here. LeetCode 70, climbing stairs, has a similar dynamic programming structure, while LeetCode 931, minimum falling path sum, and LeetCode 62, unique paths, are other great examples of problems that rely on dynamic programming techniques. When tackling problems like this, there are a few alternative approaches you might consider. Brute force enumeration, for example, is straightforward but inefficient for large values of n or k due to its k to the power of n complexity.
Recursive backtracking combined with memoization can significantly reduce redundant computations, though it may still require high space usage because of the recursion stack.
Dynamic programming with tabulation is often the most optimized approach in terms of time and space, but it requires careful thought to correctly define and initialize the states. Finally, for some problems, mathematical combinatorics can be extremely efficient, though this approach is generally limited to scenarios with a clear mathematical formulation.
Each of these methods has its trade-offs, so it's important to choose the one that best fits the problem constraints and requirements. Great job following along.
To wrap up, we reviewed the problem, discussed the dynamic programming approach, and highlighted key takeaways like leveraging DP for overlapping subproblems.
Keep practicing these types of problems to strengthen your algorithmic thinking. Thanks for watching, and I'll see you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!